morning and welcome. This is a presentation about solar energy, basically from the point of view of people who've had it installed, and then also from the point of view of one of the people working in the industry. My name is Murveit. I'm a research scientist here at Google, and I had the experience of basically paying somebody and having them install solar panels in my house. That's the typical story that most people who have solar panels done would do. David Talkin's going to come on in about 25 minutes, and he did it himself. And he put it in a house in the country without any access, normal access to electricity, and that's how he's providing electricity to his house. So totally different do-it-yourself experience David's going to talk to you about. And then we're going to finish up with Kurt, who is actually the guy I worked with to have solar panels installed in my house. And as he just said, in addition to working at Horizon that does the solar installations, he was a founding member of the Global Warming and Energy Committee for the Loma Prieta chapter of the Sierra Club, and has been working to fight global warming for the last 5 years and is really committed to this kind of technology. So anyway, with that introduction, here we go. You could take a look right here at the at the top of my house, and the solar panels that I have that are working now and producing electricity. So why would anybody here want to do solar electricity? Obviously for the good looks, right? Makes your house look terrific, makes a statement to the world that you care. You can save money by producing your own electricity. And of course, you may have to produce electricity somehow if you're like David and you don't have access to the solar panels. Here's a picture of the front of my house. It is a concern. I mean, some people say, what the heck is this? There's a recent news story about some guy who was prevented by his homeowners association to install the panels. Here's the front of my house. In my opinion, it looks terrific. But we actually did have an issue where because of the amount of shade I had around my house, we didn't have room to put all the solar panels I would like, and we actually had to put some panels in the rear, and the rear is north facing, so you really couldn't put panels on in the northern hemisphere. You have to face south for things like that, and so there it's a little more obtrusive, right? Because it had to be racked up to face the sun a little bit more. But anyway, that gives you an idea what these things look like. Before I get into the meat of the talk, I wanted to talk just a little terminology. Many of you guys, maybe most of you guys understand this, but it's good to get it out of the way just in case. The difference between power and energy and what you buy from PG&E or whoever your electric utility is. Power is measured in wattage. You could think of it as how hard something is pushing. Or, you're trying to lift a weight and what kind of force you have to put on that weight. Energy is power times time. You're pushing it for an hour. That's the amount of energy you have to put out. That kind of thing. That's the difference between power and energy. Power is measured in watts. Energy is measured in, watt hours or kilowatt hours. And so you may buy from PG&E in the course of a month, 600, 700, 800 kilowatt hours of electricity a month, and they'll charge you whatever, 10, 20, 30 cents per kilowatt hour. And that's the deal basically you have with your utility. And so, as I said, kilowatt hours is a number I'll be mentioning a lot during the talk. And this is how PG&E charges you right now. Not everybody, not Google, but most residential customers use this E1 rate schedule for electricity, and you can see they'll charge you about 11 cents per kilowatt hour at your initial usage, but then as you use more and more, the charge per kilowatt hour goes up, so that the marginal charge can be quite high if you use a lot of electricity. Before I started this project, my baseline usage was 380 kilowatt hours, and I discovered I was using 1,300 kilowatt hours a month. I wasn't paying a lot of attention to my electric bill, and I had high electric bills, and I was paying 36 cents a kilowatt hour for each marginal. If I turned something new on, that's how much I paid.
Good question. Do you use E1 or do you have E7?
Right now I don't use E1, but because I'm solar, and I'll get to that. So just to show you guys, this should be obvious, but so here you are. Here's a 650 kilowatt hour. I'm closer to this now, but user, and with a $90 electric bill, But if you just doubled that to 1,300 kilowatt hours per month, which is about where I was before I started this whole deal, you have triple the electric bill, right? So that second 650 kilowatt hours cost you twice as much as your first 650. So you can actually save money with solar energy if you tend to displace those expensive kilowatt hours. If you're trying to displace those cheap kilowatt hours, that's actually harder to make this a money-saving deal. But before you get into, I mean, basically what happened with me is I decided to do this solar panel thing. Solar, it was hot. I said, let's get into it. I call up Kurt, and I say, teach me about this. I want to buy this from you guys. And he comes over with a whole bunch of light bulbs and things like that and says, well, before you replace, you displace the energy, let's talk about saving energy. Do you really need to use all you need to do? And that's really the right idea. So I did it sort of, bass-ackwards, as they say. I would recommend that, even before you start this project, go figure out how much electricity you use and see if you can save some. And I'm going to go through what I went through. So first thing you got to know is how much you're using, and then where you're using it. And there's a number of ways of figuring that out. Obviously, you can look at your utility bill and see, how much they're charging you. It'll tell you right there how many kilowatt hours you're using a month. You can use a device like this called a kilowatt if you're curious about any individual device. You just plug this into the wall. If it has this kind of plug, you plug into that, and it just displays, 70 watts, 300 watts, whatever it is you're using. You can use your electric meter to see how much energy your house, or how many power your house is using right now. Or obviously you can look on the web and see what the typical refrigerator or whatever uses, and they're usually pretty close. There's many things that you can't really measure. What's the power consumption of my, pool or something like that, pool filter or something like that, where it doesn't plug in, it's been wired into the house. How do you deal with stuff like that? And the way I wound up dealing with stuff like that is looking at my meter. And this is the old-fashioned meter that many of you would have in your houses. And you've probably seen it, this thing spins around, and every time it spins around, it shows you a certain amount of energy used. This is the dials that tell you how much you've used. At the end of the month, PG&E comes out, they read it, they have written down the previous months, they subtract, send you a bill. The interesting thing about this is there's a little mark on this dial that spins around, and you could, there's just one mark on it, so every time it comes around, you could measure how much time one revolution took. And you can see right here on the thing, a little number 3.6. Well, it turns out that tells you how many watt hours each revolution is. And so by using this little formula, you could realize that, if it took 10 seconds to go around, that was about 1,300 watts that you're using currently right now. And and let's say you turn on a 1,000-watt appliance, that should go up to 2,300. Or if you know at 10 seconds at that, and 3 seconds is that. And so I would do stuff like that. I would turn on my pool pump or my outdoor lighting, and just notice the change. Of course, you have to be careful that the heater didn't just kick on, or the fridge didn't just kick on, and stuff like that. So you may have to do multiple measurements. But that's the idea of how you can do a little audit of your house. Well, I started doing my audit. First thing I noticed was my pool. And there's my pool pump, and it was using a whopping 400 kilowatt hours per month, because the pool guy had set it to basically filter and sweep, and these motors were effectively on 11 hours every day. This was in December. I mean, we don't use the pool in December here in California, at least in Northern California. And we were using a lot of unnecessary electricity, and I won't go into the details, but the bottom line is, in the wintertime I saved almost 300 kilowatt hours a month just turning that down. And in the summertime, a significant amount, and on average, but throughout the year, remember I started with a 1,300 bill, and I, per month on average across the year, probably got rid of about 240 kilowatt hours. And I'm telling you that I was spending over $100 a month just on electricity to filter a pool. Halogen lamps. A lot of people buy these, they're really cheap. They're like $10, $20, $30 at Costco or somewhere like that. These 300-watt halogen lamps. Amazing users of electricity. In fact, you'll figure out, I think a typical user will spend $100 a year on electricity for your $20, $30 lamp. And it's sort of a false economy. Anyway, I had a couple of those in high-use areas that I replaced, and I think I saved about 40 or so kilowatt hours a month. I did this little hack to mine where I replaced, I switched it to a non-halogen version, and I put in a couple complex fluorescents in mine. And now actually I found that you can buy fluorescent versions of these things, and that's probably the way to go. They're a little more expensive. They're maybe like $70 instead of the $20, $30, but actually over a year they're a lot cheaper. We have a lot of lighting. The obvious thing people tell you is, replace all your lights with complex fluorescents. I did that. I also found, though, that I had a lot of these fixtures in the ceilings. These are 150 watt halogens in high-use areas, and I actually went and replaced the fixtures themselves. That's a $100 investment per fixture, but it probably saved me in the long run, especially if I wasn't going to solar. It would have saved me a lot in the long run. It's probably a good thing to do anyway. In the end, I replaced around 2,000 watts of lighting in my house with about 450, but quite honestly, there's a lot of lighting left that's sort of harder to replace. Computers are another story. We have, for the 4 people in our house, 5 computers. I'm probably not the only one with that kind of ratio in this room. And, a few of them were left on 24/7. The 24/7, and I'm not even talking about monitors, just computers. 24/7 computer probably costs you, well, it's 40 kilowatt hours a month just for that one computer, and if it doesn't need to be on at night, well, you can save a lot. So anyway, bottom line of my energy conservation project, you can see at the top was my original usage, my new usage. After doing basically these 4 kinds of things was there, you can see I saved myself about 400 kilowatt hours a month. The funny part about this story is we started this project with Kurt before I did this, so I had this system designed where it was going to actually pay me back in, I don't know, 10, 12 years. But because of the fact that I saved all this energy and I didn't change the size of the system, the payback is probably marginal at best. That's not a bad thing in my opinion, But if your goal was to just make it pay back, at that point I could have used a smaller solar system, or I could buy myself a cool electric car, right? And use more electricity that way. So that's the end of the conservation part. And then let me talk a little bit, about what is a solar panel system, at least from my point of view, the layman, if you will's point of view. What do I know about that? Well, this is your basic block diagram. You have your solar panels on your roof. They generate DC electricity, not AC, not the kind that you could plug your TV into, right? So you got to convert that to AC. And you do that by these big devices, or these electrical devices called inverters. I have a pair of 3.3 kilowatt inverters. At Google, we have 150 kilowatt inverters because we have a lot more solar panels. But you get the idea. You can convert that to sort of basic house electricity, gets mixed into your electric panel, where all your electricity goes, and can go into your house, and it can go out to PG&E. If you're producing more electricity than you're using, you sell it to PG&E. If you're producing less or none, you can buy it from PG&E, and that's the basic way that the system works. David is going to talk pretty soon about what happens if you don't have a PG&E to sell you electricity. Well, you can have basically the same setup, except the panels go to some batteries that store it. In my case, PG&E are my batteries, effectively. So here's a picture of my panels. You've probably seen some solar panels, since there's 9,000 of them scattered all around Google. And I'm not using the exact same kind, but they're very similar. They're about 13 square feet, about 5 feet by 2.5 feet each panel. As you can see, they're installed in these grids, so you can pack them pretty close together. They're very sensitive to sun, to shade, and clouds. Direct sun hitting them is terrific. Cloud flies over, you can see that production shoot down. They're somewhat sensitive, not nearly as sensitive, but somewhat sensitive to sun angle. If the sun's hitting them square on, that's a lot better than an oblique angle. And they're sensitive to temperature. Sadly, when it gets warmer and the sun is better, the efficiency of the panels actually goes down somewhat, 10% or whatever. They're spec'd, if you get the spec sheet of my panels, they're spec'd at 215 watts per panel. Practically speaking, mine don't go over 155, 160 watts. So that spec is under ideal conditions, and those ideal conditions just aren't met. So don't go like I did naively when I started this project and multiply 215 times the number of panels and expect that that's what you're going to get, because you won't. The sun this is how much power the sun puts out, about 1,000 watts per square meter. You can see these panels for me are generating 155 per 1.2 square meters. So it's getting, what, 10–20% of the energy the sun's putting out.
So is the performance consistent with age, or do they degrade?
I think they degrade it like 1% a year, something like that. Kurt can mention that. A quarter percent, sorry. These are the inverters. Like I say, each of these can put out about 3.3 kilowatts. I have two because I have a 6 kilowatt installation that actually, on a typical sunny day, puts out about 5 kilowatts, in the middle of the day. And if you look at them, you can see they'll tell you, how much power right now, 2,600 watts, and that day so far it had put out 27 kilowatts. And so that's the panels, and then the inverter, and then they're connected up to your electric box over here. You notice it says this electric box is serviced by PV system. That's so somebody shuts off the utility power and goes to work on the electricity in your house and doesn't electrocute themselves with the solar panels. Right? They got to know that because the typical house doesn't have multiple sources of power. So you got to inform PG&E and stuff like that. That you have to switch meters when you install a PV system as well, and you get this new digital meter. And the reason you get this digital meter is because you're going to switch over from that electric plan, the E1 plan that we were just talking about, to a time of use plan where your rate actually varies by the time of day. That's the kind of how Google's built, and that's how you want to be built if you have a PV system. What happens in this kind of time of use is that, peak hours where there's more demand on electricity, you're charged a lot more than non-peak, as you can see. But the good news is in peak hours, that's when the sun's out. That's when you're selling to PG&E. So you get to sell to PG&E at 29, and then you buy back in the evening at a dime. So you want that. You can also see, by the way, in the winter it's different than in the summer. And again, it's just more demand on the utility in the winter. So I'm going to move on to where to place the solar panels. If you have a lot of sun and you don't have these shading issues, it's really not a big issue. You get some nice southern exposure roof. You put your panels there, figure out how many panels you want. Kurt will talk to you about that, and off you go. But as you can see from my house, it wasn't quite that easy. And in fact, if you look to the south, there are these giant, what kind of trees are those? Monterey pines, right?
They're our neighbors.
Our neighbors, Monterey pines, our favorite trees in the world. And they're right to our house, which isn't a problem in the summer, but wait until the fall and the sun angle gets lower in the sky, and those things are going to start shading my panels, and my production will go way down in the fall. To the west, there's these trees. So in the evening or the late afternoon, I'm going to lose a lot of energy by that. To the east, so in the morning, I lose some. But I do have some sun in the middle of the day. That's enough to make this project worthwhile. So how do you figure out where to put the panels? There's a picture of Kurt, who's going to be talking to us on my roof, surveying the roof, trying to figure out where the heck to put the panels. How does he do that? You see this device called the Solar Pathfinder. We have one here you could look at. More or less, you put it down and level it, and you can see, well here on the slide there, you can see what the sun, what part of the sky will the sun be hitting this part of your roof at what time of day, what month in the year. So for instance, over here you can see that at 1 o'clock in September it's sunny, but at, right there at 9 a.m. in September, it would be behind that tree. And more or less, you can survey your roof and decide where. And you can see that those trees that I had in the, whatever part of the sky that was, in the southern sky, I guess, the western sky, are causing a lot of shade during that part of the year. And you can see right there, I'm losing electricity. And I believe, in the end, my entire solar system is only about 60% as efficient as it could be because of all these trees. So Kurt did an analysis of this thing and came up with a prediction of the performance of my system, and there it is. The lighter part is the prediction, and the darker part is the actual performance for the 4 months I've had the system so far. And you can see he's pretty much right on. And there was actually some panels that went, an inverter that went down that month, so that's actually was pretty close to the prediction if you correct for that. Installation was a snap. I mean, more or less I paid the money, it was installed in a few days, no issues. It was great. I talked about the rear panels having to be installed on these racks. I want to show you the effects of shade. You could see at 10:15 and at about 3:45 this time of year, I'm out of the sun starts shading a panel. By the way, once 1 or 2 panels are shaded, panels are wired in like strings of 8 or 9, or at Google there are 14, I think, and they can be as low as 6. But anyway, you have these strings that are in series and then connected in parallel. If 1 or 2 panels is in even a little bit of shade, that string is more or less gone. That's just the way they work, and I'm not sure of the reason. But anyway, you can see as we're coming out of the sun at 10:15, we start to go up to full power, for that, as much power as it's going to get for that time of day, and it lasts pretty well until the sun hits those other trees that I showed you, and we get shaded there again. So shade is a significant effect. Clouds, different kind of shade. Instead of the tree, you're shaded from a cloud. Big deal. Here's a clear day, here's a cloudy day. Can you see a difference? Obviously, there's a lot of cloud that part of the day. An interesting factor, though, is you'll see it actually peaked higher over here than it did. Well, that's the wrong slide. Sorry. Well, whatever. You saw it peaked higher over there. It doesn't seem to want to go back. And so I think that's because of the temperature. I think it's actually cooler on the cloudy day. So when it was in the sun, it was moving. We're back. Okay, let me talk about, oh yeah, damn. I wanted to talk about temperature. Again, another example of temperature. One day I went on my roof and I cleaned off my panels, because you get this new set of solar panels, you're so cool on keeping them clean, is the pollen messing me up? The answer is no, the pollen's not messing you up, but when you go on the roof and you hose down your solar panels, what happens is you cool them off. And you can see there, by cooling them off, I actually have this big spike in performance. It just shows you how temperature affects things. I built this monitor for, so going on my local website where you can see the performance of my system. I wanted to give you an idea of what my system performs like for the course of a couple months, so take a look at this. Here we are at the start. This is the end of May, start of June, and you can see we have some clouds and whatnot. Those things are little glitches in the inverters, by the way, that sun power is going to come and fix for me. It's only costing me about 0.5% overall in performance, but you can see them in there. After a while, starting about here, we're now mid-June, things are pretty sunny, and they stay sunny pretty much for the rest of June and July. There was another cloudy day, but you get the idea. Performance for me stays pretty close to 30 kilowatt hours a day. And there you go. This is the performance overall over the year. We had a cloudy April. That's when one of my inverters went down. I went to half power. And then more or less since then, until yesterday, things were pretty good. My last slide just shows you, when I announced this presentation, I got several emails from people showing that they too had installed solar systems, and a few of them had put up solar websites. And so these are sites, the top 3, mine, Dan Halem's, and Steve Lacey's, who may or may not be in this room, I don't know what they look like, are their websites, so how their solar systems are doing. I'll leave this up for a minute. David, get ready. I'm ready to switch over to you. This is, of course, our Google system that shows our, I have 32 solar panels. I didn't mention that on my roof. Google, has 9,000. So, about a factor of 300 more. And so we, of course, you've probably heard, have a web page that shows the performance of that system. So with that, David, are you ready to take it away?
Yes, indeed.
Okay, go for it.
So, greetings. I'm going to talk about a system that we have installed in the southeastern United States, in Virginia, at my country place. We actually have a bit of a history on it. We've been tinkering with solar since the 80s. We've only recently gotten serious about it. About 3 years ago, we built an octagonal cabin, and we put in a proper well and put in a 240 watt direct solar pumped well. So it's a deep well pump that does not involve batteries or anything. It just pumps directly into a tank and stored, then the gravity feeds the tank to the house. We have a 480 watt battery inverter set up for that little cabin, and it gives us enough electricity for our refrigerator, computer, lights, and so forth. I have a satellite internet link, so I can actually work from down there. And that old inverter that we have is a so-called modified sine wave, and I'll talk more about that later, but in general, that's to be avoided. You want to get a true sine wave inverter. And we're now in the process of building a full-sized house, and that's really where this particular story begins. So there's the old cabin that we built in 2003, and it's just a one-room eat-in kitchen, basically, where we have parties and hang out when we're camping. And there's the 480-watt array with its little set of batteries and inverter on the pole there. There's a primitive charge controller that keeps those marine batteries charged. That's a 12-volt system, so it converts from 12 volts to 110 volts AC through that modified sine wave inverter. Now, our new PV system was, the motivation behind it was that the contractor wanted power for his power tools, and we actually DDR off the grid down there. And nobody wanted to listen to a generator drone on throughout the construction. And I thought it'd be kind of cool to show the construction workers and others in the area, other locals, what could be done with solar. So we decided we'd order the equipment beforehand and whip down there and quickly install a temporary system so the contractor would have power. So I found a really good deal on 180-watt modules. I bought 30 of them. They're 24-volt modules. We're going to run them at 72 volts DC. That'll be input to the battery charger. That's 3 of the panels in parallel, and we'll put 10 in series, 3 of them in series and 10 of them in parallel. So it'll give us 72-volt input to our battery charger. The batteries themselves will be a bank set up to be a 48-volt battery bank. We've got a maximum power point tracker. I didn't touch on what that is. It's a very important thing. Solar panels are basically constant current devices, almost perfect constant current devices. So the amount of power you get out is dependent upon what voltage you're pulling it out at. So you want to pull out as close as you can, really, to their to a high voltage, something close to their maximum voltage. Usually about 75 or 80% of their maximum voltage. So the maximum power point tracker is basically an impedance matching device between what the panels can output and what the batteries and other things can sop up. And I'm going to use on the house 24 kilowatt hours of storage. That'll be 12 of these marine batteries, 115 amp hour batteries. And they're rather cheap. I get them at Costco for about $60 a pop. For the temporary setup for the contractor, I'm only going to install 10 of these panels, so that'll be 2160 watts. And I'm only going to have 8 kilowatt hours of storage, because that'll be plenty, since they just use it in short spurts. And I got a couple really nice heavy-duty pure sine wave inverters. Now, they're not really pure sine wave. They got about 5% harmonic distortion, but they're really amazing inverters. They're 3,600 watts each. I got 2 of them. They can be hooked up out of phase, so you can get 240 or 110 out of them. 240 or 120 volts AC out. So here's a sort of a block diagram for those of you who may not be familiar with this system. So you've got the photovoltaic array, which, as I say, is sort of a constant current source, which likes to put out its voltage put out its power around 72 volts. You can short it down to 0 volts, and you still only get slightly more current. So you want to keep it up close to that 72 volts. That's what the maximum power point charger does. It impedance matches down to the 48 volts that the battery is going to use, and it also has a very fancy control logic that keeps the batteries happy. Lead acid batteries are very finicky, and you can easily damage them if you don't charge them properly, quickly, and promptly. Just leaving a battery set flat overnight is enough to take years off its life. So the batteries themselves in the ultimate system will be 24 of these 115 ampere hour 12 volt marine lead acid batteries, hooked as 4 series 6 parallel to give me 48 volts with a lot of storage. The batteries then, again, their voltage is 48 volts, and that's the input DC to the inverter. And the inverter is set up with an auto transformer, so I can only have one inverter on if I want, and I can still get 240 volts, or if the load demands it, both inverters can come on and supply up to 7,200 watts, of course, until the batteries go flat. And the rest of these, most of the rest of the slides there, I'm just going to show you the legacy of putting in this little temporary setup for the contractors. We dug 10 post holes, stuck in these treated posts, and used 1.25 inch conduit for the rails that will eventually put the panels on. This is all stuff you get at Home Depot or Costco or Lowe's or whatever. And there we had a little bit of a comedy act because an 18-wheeler pulled up at the end of the country road and wanted to unload the panels. Of course, we're about 4 miles from there. And so we had to slide the 1,300-pound pallet off of the lift gate of that 18-wheeler onto my friend Nick's truck there. And my heart was in my mouth most of the time. So that's 30 of the panels at around 1,300 watts, 1,300 pounds, including the weight of the pallets over. So these are the 12 that we pull off the stack now to use for the temporary setup. And that's what it looks like when they're lashed to those rails. And we bought a trash can cover and put our electronic gear in. And off the side there you see typical equipment that the contractor's going to use. And in fact, we tried our best to short out the inverters and see if there was going to be any trouble. And so I got that Boss Stitch 2.5 horsepower compressor and basically got it almost pumped up to its working pressure of 120 pounds, and then plugged it back in again. And when you do that, that basically puts the maximum pump load that you can possibly ever have on it. So I did that while I was ripping with the 7¼ inch burn drive skill saw, which also draws about 13 amps when you kick it on. And the inverters didn't even grunt; they just performed beautifully. So here's a larger scale picture. You can see inside of the trash can cover the 2 Outback inverters, and the big box on the left is the AC output, and the box on the right is the DC input switching and DC shunts and other things. At the top up there, you can see laying on the side maybe the Outback charge controller, and that's the, as I say, the impedance matcher between the panels and the batteries, and also keeps the batteries happy. And then here's a closer up picture of the same thing. And I can't really recommend this Outback stuff too highly. It's just a joy to use, very robust. At one point I had the inverters wired up so they were in phase instead of out phase across that auto transformer, which means that they were dead short driving into one another. And I switched the thing on with the air compressor on it, and it grunted a little bit. One of them decided it was going to pack it in. It turned itself off, and then the other one started up the compressor just fine. And I did that about 5 or 6 times till I figured out what was wrong, and then I wired it back, and everything was just wonderful. So here's the finished setup there, and that's what the contractors are plugging into, and they've been using it now for about a month and a half, and it's just been fine. They keep bringing new things over to plug in, see if they can break it. And there's my house under construction. It's actually now got walls on it. So what did we learn? Well, when I thought about bringing up this temporary setup for the contractor, I thought it would be a piece of cake and I'd have it all done in a couple of days. My friends spent 4 hard days together, and then I spent another 3 days by myself tidying it up. It was a lot of work. Something's bound to go wrong. In our case, the worst thing was the glitch of having the stuff delivered 4 miles away and dumping it off the back of an 18-wheeler instead of having it delivered to the site. A few other minor things, but don't go into something like this thinking everything's going to be smooth. Always estimate longer than you think it could possibly take. And pay for good components. I've been through a number of cheap inverters and charge controllers, and having worked that Outback stuff now, I'm a convert to good equipment. And by all means, use pure sine wave inverters, because the so-called modified sine wave, they put out a certain amount of wattage for sure, and if you're heating water with it, using a resistance heater or something, sure, you get that much wattage, but if you're driving an inductive load like a refrigerator or something like that, the power factor is terrible, and it makes the motor run hotter, and you don't get anything like the kind of actual power transfer you'd like to have. Shop around for prices. I ended up buying my panels for about half the going rate, and they're very fine panels. Learn about battery care and feeding. It's sort of the common lore in off-the-grid systems is the first time you get your battery pack, you're going to install the thing and run your batteries, and then you get another set of batteries. Start out by learning how to take care of batteries, because they'll last a relatively long time if you take care of them, and you can run them overnight, literally, if you don't. But in summary, off the grid really, really works, and as Hy pointed out when he was starting to set up his system, having this solar power available on site really makes you think about where the energy comes from and where it's going. So that's really all I have. Can we switch over?
Can you hear me okay? Okay. There we are. Start my presentation there. Okay. We'll come back up in a minute. I'm just looking at a blue screen anyway. Let's see, do you press the arrow key to
Oh, you're looking.
see which one here I can see enter for next. There we go. Okay, yeah, I'm Kurt Newick, founder of Global Warming Committee with the Sierra Club and blah blah. This is what shading does. I'm going to go back here. Hopefully it'll go back. Does P go back? This is shading on a cloudy day. Shading is very important and very sensitive. On a cloudy day, it doesn't matter that much. Here, I'm going to go back. P should go back. Huh? Doesn't want to go back. Arrows go back. Yeah, okay. There's shading on a cool day. Okay, just go back one. All right. This is just a little pine tree that shades the array. These are two inverters. It's normally a bell-shaped curve. This is time on the x-axis and power on the y-axis. Just a little bit of shade that stripes the array, knocks out the production 40%, peak production. So I wanted to drill that into your head to get a good shading analysis. Very important if you learn nothing else. This is the same array in a cloudy day. On a cloudy day, there is technically no shade because the sun scatters in the clouds and comes down evenly. So on that same array, it only loses 14% of its energy on a cloudy day. So if you have some shade in the winter, it's not as big of a deal because it tends to be rainy and cloudy. I'm just going to breeze through some pictures. There's triangular modules fitted on a hipped roof. There I am on a roof with the boss. That's what they look like on the installations. This is a wood shake roof. You can compare this. They look nice when they're in even rows, and compare that with that. So this is a strip mining coal operation. That's a valid comparison in aesthetics. I love that picture. I had to throw it in. I pressed the arrow key twice, so it's going to storm through twice. I'm trying to get off this. It's not my goal to stay here. But anyway, the next picture, I guess it just takes a minute here. Now we'll be 4 slides ahead, so you guys are going to have to speed watch these when the computer catches up to us. But it's going to be a sun power installation. I'm going to go through at the end. I have a fact sheet over here. Anyone wants to size them? There's a technical formulas I created myself. Okay, here's a solar arbor. Okay, that's our best looking system compared to the previous slide. We built arbors too. Okay, I'm just going to have to wait for the computer here. What's the story of our life? Wait for a computer, right? These are the important benefits of solar. Rising electric costs are avoided. Solar costs less upfront. When you finance it, anyone over $100 a month for your electric bill, it's going to cost you less money to take a loan and pay that than you own the systems, like owning the house. Investment is recouped upon resale. So your principal's protected because when you sell your house, it'll be worth more than what you paid for the system. And the really kicker is this appreciate over time. So your savings increase over time as the cost of electricity goes up, and I'll have a graph to show you that. The most important thing of all is not money in my book. It's the success of the human species. If we fail to put in solar, we may fail as a species. That trumps everything in my book. PG&E solar payback rates in graphic form. Holly had a great thing in the summer. You can see it's 29 cents a kilowatt hour, noon to 6, 3.5 times the rate as when you use it at 9 cents in the summer. So you can size the system 38% smaller in a south-facing sunny array, 38% less cost, and still zero out your bill using a time of use rate schedule. It's huge. That's why so many people put in solar in California. Net metering is just when you get retail credits. When your meter goes backwards, you get credit at the retail rate, whatever that is. And the summer excess can be applied to winter. It's on a true-up annual billing cycle. And you get a 3-to-1 ratio during the summer. When the meter goes backwards, it's 3 times as fast as when it goes forwards because the credits are worth more, and you get full retail credits. This is how much solar costs. This is what the great way to look at it. I love this slide. It has 3 different users. One 600 kilowatts hours a month, which is low normal. One is high, medium high, and one is very high, 1,450. So you see the highest user was paying $326 for their electricity every month, and the system costs after rebates, you could probably go less than that with the sun power, but conservatively $47K. Over the course of 25 years, you spend $47K up front, After 25 years at 5% electric price inflation, you'll have saved $158,000 for the big system. And that's at 335% of what the system costs. Most people are closer to one of these two, the medium or small, and I just love that slide. I'm going to go to the next one. This is why I put in solar. I also love this one. Look what electricity costs in 1970. That's 2 cents a kilowatt hour. Look what it costs now. Well, it depends on what you're paying, but on average, it's about 14 or 15 cents a kilowatt hour. So, and that's going to continue that long-term trend as fossil fuels run out. So you're really protected from this kind of thing with solar because it's free to operate once you pay for it. I'm going to wait for the computer now. I guess I use the arrow keys. So I just want to make a plug for my class on August 25th. Here we go. This is how to size a system. Pick up the fact sheet on the back. Basically take your annual electric usage, and here's the formula, in AC watts of the system size, you divide it by 4.4. So your average daily electric load, divided by 4.4. Let's go through the formula. 20 kilowatt hours a day is normal. Divide that by 4.4. So to generate as much power as the average retail electric user needs, you'd need a 4.5 kilowatt AC system size, or that's without a time use meter. To zero out your bill with an E7 PG&E time of use meter, you divide your average electric load by 7, and you can actually put in like a 2.9 kilowatt AC system size, and you'll have a zero bill at a substantial savings over a 4.5. So there's kind of two ways to look at it. Those are the formulas. Many people have their own. This is assuming San Jose, California, which gets the equivalent of 5.4 peak sun hours in the south-facing sunny array. If you're facing a different direction and a different location, it may be different. This is my class, August 25th. I go through tons of details. It's a great class. You're welcome to come to that. And that's what I have. So we'll have questions now, I think. So who's first? Yes.
So if you have...
Oh, one sec. Do we have a microphone to pass around? Or well, Ben Kirk, you don't have one.
That's all right.
Well, you can use mine, I guess.
Yeah. If you have $10,000 to spend and you want to save the world from global warming, how effective do you think getting solar panels on your house is compared to other things you can invest the money in?
Great question. I'd say it's all individual, depends on the person. Solar powers renewable energy and it's the solution to global warming. It's the way to create power responsibly. If you can do things to save energy, it might be cheaper to conserve, but eventually you're going to have to get your power from somewhere. And I'd say wind power, solar, any renewable energy is the source that you want.
By the way, David, just is David's microphone on? Feel free to pipe up if you do want to answer these questions.
Okay, will do.
Who's next? Okay.
Can we pass the mic?
Pass the mic over here.
I wanted to ask, I guess, David and Kurt about the lead batteries and their lifetime and if there are other better solutions for
Well, really the only way to, I guess this is on, batteries are great if you're off-grid. If you're on-grid, I'm really against them. I'm not a fan because they are expensive, they're inefficient, they wear out and they're toxic, that's why. But if you're off-grid, they're great. They're, you can just care for your batteries. Do you want to talk about this on the other side there in New York?
Sure.
Yeah.
Sure. Carefully taken, if batteries carefully taken care of can last about 5 years. And they're actually amazingly recyclable. When you return the battery as a core, and when you get your new battery, there's no additional pollution to speak of at all in turning that back into another battery. So they're pretty ugly things. And I resisted for years getting involved with batteries. That's why my original water pump setup was a direct solar. And I spent a lot of time plotting and scheming how I could build refrigerators that would be direct solar and everything else. But I acquiesced to batteries because otherwise you're talking about buying a lot of specialized or inventing your own specialized equipment that costs much, much more than the standard equipment and doesn't really have the payback. For instance, you can get a refrigerator that's designed to be direct solar, but the refrigerator alone, for a very small capacity refrigerator, something like 5.5 cubic feet, costs around $1,600, and it requires DC brought right to the house. So now you're talking about big, fat copper wires to bring the DC to the house versus having the batteries. Well, copper mining is a problem as well. So I hate batteries, but I just don't know what else to do. And keep in mind that there are new battery technologies coming online that are more efficient than lead acid. The lithium ion and the nickel metal hydride batteries are showing a lot of promise. So yes, I agree, batteries are great, but off the grid, that's what you got.
Yeah, they're working good and they're perfected. The lead acid ones you have are great, long life. They'll go 10, 15 years. Another question. Pass the mic over here. Go ahead.
So I have a solar system, and actually it's my second system, second house. And I had E7 for a while, and I thought that didn't really work for me because I was consuming more than I was producing. So I never had the pumping at 3 times and whatever. You have a comment on that? So what I have now is I have a solar system and I'm using the E1.
Depends on the size of your system when you use energy. If you're welding in the afternoon, you don't want E7. It all depends. Everyone uses energy different times. I reprogrammed this pool to run at different times, so he tries to conserve noon to 6. 95% of the people we deal with get the E7 rate schedule. Some people may not care about bills. They'll put in a bigger system, 38% bigger. You don't need E7. You can generate as much power as you want. You just put in a bigger system. But almost everyone puts in E7s to their benefit, unless you're welding in the afternoon. Or you maybe have too small of a system or something. I'm not sure. We can go over that offline if you want. Another question.
One sec. I just wanted to mention, so in our system, but it's sized a little bigger, we're significant producers in the afternoon, noon to 6. And right now in the summertime, when I turned on my pool pump, I upped the pool pump, we're actually slight consumers of electricity overall. But, it's strongly producing, and so for us, it works out. I'm a little worried actually in the winter, see how that goes.
Yes. So you mentioned the importance of the angle of solar panels. So if I have a house where the roof is pitched, let's say this is south, is there basically no hope for me?
No, west works great too. The highs facing west. West or south are equally good financially. South will outproduce over the course of the year, as long as it's not too steep on the west. A 4 and 12 left pitch is really very, very good. But east you want to avoid because of time use rates. You want it to face the afternoon sun. West is fine.
Let me just add that, can I add to that comment a bit?
Go ahead.
You don't have to be too worried about whether you're 5 degrees off one way or the other. The computation is actually quite straightforward. It's the cosine of the error angle, that is to say the error from the normal, is really all you have to worry about for moderate angles. Anything up to say 15, 20 degrees off, the losses that you're going to see is equivalent to the cosine projection onto that panel.
Yeah, and to add, my 2 arrays are sloped significantly differently, right? So the one that was on the back is what's like a 5% slope, and the one on the, facing the west is more like a 20% slope. So, and you can see that, so the back array is better in the mornings, which is optimal from a PG&E point of view. Maybe from a global warming point of view, it's irrelevant. But from a PG&E point of view, it's a little different. But, it's okay. I think that's the minor effect, as long as, you're in general facing the right directions. And the major effects are clouding and things.
I'm interested in the solar cell industry itself and how the $9 to $10 might change over the next 5 years, if you're thinking about it.
Yeah, the cost of the equipment's gradually going down. The rebates are going down 2 to 3 times faster. So if anyone's considering solar, get your estimates right away. And that's been true. Best time to buy solar was 3 years ago. The rates were $450 watt rebate, and the equipment cost has actually gone up a little bit because demand's so high. But I think it's kind of peaked now. There's been a huge, long downward trend of panel prices over the last 20 and 30 years. Now they're kind of leveling off and they're gradually going down. And they will continue that depending on supply and demand, but the rebates in California go down 2 to 3 times faster than the cost of the gradual decline.
How much of the $9 to $10 is equipment cost versus labor?
Oh yeah, the equipment, the solar panels are about 60% of the cost, the inverters about 10%, and everything else is about 30%. The rails, the electrical, the installation, the permitting, the inspection, all the other whatnots is 30%.
Can I just add that my off-the-grid system has ended up costing me around $4.50 an installed watt, plus a lot of bark shins and bruised knuckles and
Another question over here, go ahead.
So I have received few bids, and two of the bids are almost exactly the same. The only difference was that one company is using BP panels and the other is using sharp panels. So are there any difference?
Those are both great panels. It doesn't really matter as long as they're crystalline technology. Any of the major manufacturers have fantastic products out there. Those are all reputable manufacturers. Sharp, I personally, that's my favorite between those two, but I don't want to say bad things about the other company. But the Sharps are very, very high quality in my opinion.
I'll mention, at Google here we have the Sharps on the roof. My house has these SunPower ones. They seem to work fine. My issues have never been in the arrays. I don't know if anybody here is from the solar project, but I forget. They installed 9,000 panels. They have a pretty good idea of how many of them malfunctioned. I seem to remember hearing like one or two. So the products seem pretty good. I'll say this about that though, about picking contractors. We got two bids too. I got one from Kurt and I got one from Solar City. And I'm sure it would have been fine either way, quite honestly. I wound up picking, who my gut told me would have been easier to deal with. And maybe Solar City would have been fine too. But I just got more warm fuzzies. And the truth is, things do happen in the project. Kurt and I were on the roof for 3 hours one day changing our design. I think in the end, if you see small differences in prices, pick who you think, for you is going to be easy to work with and work with them. But I think the good news is that probably most of the contractors around here are quite good. I know a lot of people, for instance, who got Solar City jobs done and they're very happy. So I could go either way.
So just a comment there, I have my panels coming in through Solar City and they seem pretty good. Certainly shopper. Sorry, I'm getting my solar panels in through Solar City and they seem pretty good. I'm sure definitely shop around, but what was my comment? I forget, sorry.
All right, we'll chime in when you got the mic there if you think of it. Yeah, the solar contractors are a very responsible bunch of people. People go into the business because it's the right thing to do, not to make a lot of money. So their heart's in the right place. When you're choosing a contractor will depend on experience. Trust your gut. Interview your contractor. Find out their credentials, what their experience is, and then trust yourself and go for it. Because I don't think I've rarely heard of horror stories. I don't think I ever have. People have different levels of satisfactions with different solar contractors, but there's really no horror stories that I've heard of.
My comment was that the panels themselves, they generally have manufacturer warranties of, what is it, like 20 years? And then the expected lifetime of the panel is more like 40 years. So, and also, I don't know how many companies do this, but probably a fair number also have the installation guarantees for a certain number of years as well.
Yeah, it's required 10-year installation guarantee with the California Solar Initiative, and the panels are 20 to 25-year warranties, and they'll go 40+ years.
I wanted to just put up a quick slide about the question on solar angles. I mean, angles to the sun for a second. If you can see here, you can see my two arrays, the green line and the blue line on the bottom, right? So the green line is the front array that's tilted 22% toward the west, I guess, and the blue line is like whatever, 8% toward the west. And I actually have 18 panels in green and 14 panels in blue. And so you could, it should be, there should be a big difference in the production rate. There are more panels. You can see as, in the earlier part of the day where the sun angle is favoring the blue panels, you see they're about equal. And then you can see as the sun moves west, in fact, you do see the difference. And you could also see, it peaking, as this one's facing more straight up, it's peaking, closer to the middle of the day, whereas this one is, tilted to the west, and it's peaking later on in the day. So you can see the effect of sun angle right here. And, there is a, between, let's say, 2,000 and 2,600, you know, there is a difference that it makes in your production, but it's not like, you know, if you're 20 degrees out, you go down to half power or anything like that.
Go ahead.
Notice you guys talking about maintenance. How often do you clean your panels, and do you have to scrub it, or just hose it down?
So I don't think, quite honestly, I mean, I've only had them for 4 months, and quite honestly, I don't think that there's a big effect on that yet. You know, I've heard that Google made the decision that it's actually cheaper not to scrub the panels, that, you know, the loss of production that they get from whatever, you know, winds up on those panels up there is minor compared to the cost of hiring people to go up there and clean them somehow. So I think Google made that decision. You know, for me, I'm pretty sure that when, you know, in the fall, when we get all sorts of leaves and stuff like that, it might be worth my while to go up there. And, you know, I've got the trees to produce those leaves, and perhaps Google doesn't. But I think in general it isn't. I had, you know, being a new solar owner, I showed you that slide where I was intent on keeping them clean, and I went up there, and sure enough, I got this big gain in performance. And then a half hour later, the gain was gone, and like I say, that was all cooling, and it wasn't cleaning.
Let me just say that the 480 watt array that I've got down in my country place has never been cleaned. It's at a slight pitch that you saw, and just the rain is enough to wash off the pollen and so forth.
Talk about issues related to tracking systems that will track the sun.
Yeah, that's more important if you're in an off-grid application in northern latitudes around here. It's really a waste of money. It will get, you know, maybe 25% more power, but you've got moving parts, something to break down, and you can really, I recommend people just spend that extra money for the tracker and put up more solar panels. You'll be much better off. It's maintenance free. Once you put in the panels once, you forget about them. How often should you clean them? You know, some people once or twice a year in the summer in California, just hose them down. That's what we recommend. You do get, you know, 5% more if they're really dusty. We've seen 10% hit if it's very dusty locally here. So trackers are a waste in my personal opinion. We've installed them before in the past. They're really good if you're in northern climates or you're trying to optimize winter sun. But in the summer here, optimizing winter sun is not really that financially, you know, beneficial because the rates are a lot lower in the summer.
I completely agree with Kurt. Just spend the extra money on more panels.
Is there a mic?
We have another question here. Go ahead.
Yeah, you mentioned cooling, the cooling effect, and the fact that we got a surge in production. Has there been any research into looking at, you know, setting up maybe a sprinkler system that cools the system? I mean,
you know, funny that you asked.
Serious question.
I won't answer the question directly. I'll let Kurt take that. But they also sell pool heaters. I mean, pool warmers, right? That's their business. In fact, I guess they went into business originally doing that. And so, you know, I suggested, hey, make this combination pool warmer solar system, you know, and then the pool will cool off your panels, and it's a win-win. And Kurt and Bruce both came back and said, are you crazy? You know, mix water with high voltage or high power electricity. You know, what a terrible idea. But I think there actually are ideas like that. But go ahead.
Let's see, what was the question again? I'm sorry, I was just
Cooling down your panels.
Cooling down. Yeah, there's that's done. You know, there's a gas station that does that. You know, every 20 minutes it comes on in the Central Valley, and they get better performance because water's free over there. That's one of the benefits of solar that requires no water. So you do, you know, hose them down. It goes up temporarily, but it's a very minor thing, and most people don't do that. And no, I don't know of any product out there, but you just put some sprinklers up there if you want to do that. But you know, you want to be careful that you don't thermally shock your panels because they get very hot, maybe 150 degrees in the afternoon. And if you spray a bunch of water in the afternoon, that'll cause them to cool down rapidly, and that'll cause expansion and contraction over time that may weaken some of the wiring in them. So I don't know if you really gain anything. You're just going to maybe cause problems in the long run by cycling those thermal expansions and contractions more.
Did you say?
All right.
Thank
you very much.
Thank you very much.